Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights, after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Tonight, let's sit together by the warmth of understanding and explore something that might seem puzzling at first. Across the technology world, billion-dollar companies are giving away their most valuable AI models and tools, freely sharing what took years and enormous resources to create. This isn't a sudden burst of generosity, but something far more strategic and complex. Like that master baker who shares their recipe while controlling the mill, these companies are playing a deeper game. Let's gently unpack why Meta, NVIDIA, and others are giving away the store and discover the hidden catch that makes it all make sense. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Picture a master baker who decides to give away their bread recipe for free. Not out of generosity, but because they own the only mill in town that produces the special flour needed to make that bread perfectly. This is the essence of open source strategy, a counterintuitive business approach where companies deliberately release valuable intellectual property to the public, not despite their competitive interests, but precisely because of them. When we see major tech companies open sourcing their AI models, machine learning frameworks, or development tools, they're following this same logic, the baker's logic, where giving away one thing creates overwhelming demand for another thing they control. The foundation of this strategy rests on a principle economists call commoditizing your compliments, which works like a gardener who freely distributes seeds to every neighbor on the block, knowing that all those new gardens will create demand for the specialized fertilizer and tools that only the gardener's shop can provide. A compliment is any product or service that makes your core offering more valuable, the way that widespread adoption of web browsers made Google's search engine more essential, or how the proliferation of mobile apps increased the value of smartphone operating systems. By making compliments cheaper or even free, you expand the total market for your primary business, sometimes dramatically. Consider how this plays out in the AI landscape, where the relationship between different layers of technology resembles a busy harbor where ships of all sizes need different services to operate effectively. The foundation models, the training frameworks, the deployment infrastructure, the specialized chips, the cloud computing resources, they all complement each other in complex ways. When a company like Meta releases Llama models as open source, they're not primarily trying to compete with OpenAI on model licensing revenue. They're trying to commoditize the foundation model layer so that the real value and the real profits flow toward the infrastructure and services where they have advantages. This infrastructure advantage becomes clearer when you think of it like a highway system where one company builds and maintains the roads, then encourages everyone to drive on them for free, knowing that all that traffic will need gas stations, repair shops, and rest stops along the way. Cloud providers like Amazon, Google, and Microsoft have massive computational infrastructure that generates revenue whether you're training models, serving them to users, or building applications on top of them. When they open source AI tools and frameworks, they're essentially building on-ramps to their highways, making it easier for developers and companies to start projects that will eventually require significant cloud resources to scale. The developer ecosystem effect amplifies this strategy through what resembles a thriving marketplace where the market owner provides free stalls to attract vendors, knowing that a bustling market draws more customers and generates more transaction fees than a sparse one ever could. Open source projects create communities of developers who learn the tools, build expertise, contribute improvements, and eventually become advocates who influence technology decisions at their companies. These developers become a distributed sales force essentially, though they don't think of themselves that way, recommending and implementing solutions they know well when they face technical challenges in their professional roles.
The network effects here compound over time, much like a coral reef that starts with a small foundation but grows as each new organism makes the environment more hospitable for others, creating a self-reinforcing cycle of expansion and diversification. As more developers adopt an open-source framework, more tutorials appear, more third-party tools emerge, more companies offer related services, and the entire ecosystem becomes more valuable to everyone participating in it. This creates switching costs that go far beyond the technical, since moving away means leaving behind not just the technology itself, but the entire community, knowledge base, and surrounding infrastructure. The regulatory dimension adds another layer of strategic value,
operating like a lighthouse that helps ships navigate safely through foggy conditions, while also serving as a visible symbol of the lighthouse keeper's commitment to safe passage for all vessels. In an era where governments worldwide are scrutinizing big tech companies for monopolistic behavior, open sourcing key technologies demonstrates a commitment to openness and competition that can influence regulatory sentiment. It's much harder to argue that a company is creating unfair barriers when they're literally giving away some of their most valuable assets.
This regulatory positioning becomes especially important in the AI space, where the technology's potential impact has captured the attention of policymakers who might otherwise have limited technical understanding, much like park rangers who need to make decisions about trail access based on safety considerations, even when they haven't personally hiked every path in the wilderness. Open source AI development allows for broader scrutiny and research into model capabilities, limitations, and potential risks, which can help inform better policy decisions while also demonstrating that the releasing company supports transparency and responsible development practices. The talent acquisition benefits of open source strategy work like a master chef who hosts public cooking classes, knowing that the best students will want to come work in the restaurant where they can access professional-grade equipment and learn advanced techniques not covered in the free sessions. Top engineers and researchers often prefer working at companies that contribute meaningfully to open-source projects, both because it enhances their professional reputation and because it allows their work to have broader impact beyond the company's immediate commercial interests. This helps companies attract and retain talent that might otherwise choose academic positions or startups. The data collection advantages embedded in open source strategies resemble a weather station that provides free forecasts to the community, while gathering atmospheric data that becomes more valuable as more people rely on and interact with the service. When companies open source AI models or tools, they often gain insights into how these technologies are being used in practice, what modifications developers are making, what problems they're solving, and what limitations they're encountering. This feedback loop provides invaluable information for improving future versions and identifying new market opportunities. Timing becomes crucial in open source strategy, operating like a farmer who must decide when to harvest crops, balancing the risk of waiting too long against the benefit of letting them ripen fully, while also considering what competing farmers are doing in adjacent fields. Companies need to open source technologies at the right moment in their life cycle, typically after they've extracted significant first-mover advantages, but before competitors develop superior alternatives. Too early, and you give away potential profits unnecessarily. Too late, and the gesture loses its strategic impact because the technology has already been superseded. The competitive dynamics shift dramatically once open-source strategies are in play, resembling a chess match where one player decides to show their next 3 moves to everyone watching, fundamentally changing how all the other players must approach the game. When one major company open sources a significant AI capability, it forces competitors to respond,
either by open sourcing their own technologies, by focusing on different layers of the stack, or by doubling down on proprietary advantages that can't be easily replicated. This can accelerate innovation across the entire industry while also reshaping competitive boundaries. The ecosystem orchestration that successful open-source strategies require resembles conducting a symphony orchestra, where the conductor provides the sheet music freely to all musicians, knowing that the real value lies in the coordination, interpretation, and performance that brings all those individual parts together into something magnificent. Companies need to actively nurture their open-source communities, providing documentation, support, governance structures, and clear roadmaps, while also maintaining enough control to ensure the project serves their strategic interests. This balance between openness and guidance requires sophisticated community management and long-term commitment. Risk management in open-source strategies involves considerations similar to those of a bridge engineer, who must design structures that can handle not just the expected traffic, but also the unexpected loads and usage patterns that emerge once the bridge becomes integral to the transportation network. Companies must consider how open sourcing technologies might enable competitors, create security vulnerabilities, or lead to loss of control over critical standards. They need governance mechanisms, contributor agreements, and clear policies about what remains proprietary versus what gets released. The measurement of success in open source strategies requires metrics that go beyond traditional business indicators. Much like a librarian who evaluates success not just by the number of books checked out, but by the research breakthroughs, educational achievements, and community connections that emerge from making knowledge freely accessible. Companies need to track adoption rates, community health, ecosystem growth, talent attraction, regulatory sentiment, and long-term strategic positioning, not just immediate revenue impacts. The benefits often compound over years rather than quarters, requiring patience and sustained investment. As the AI landscape continues evolving, open-source strategies will likely become even more sophisticated, resembling the complex root networks of a forest, where trees share resources and information through underground connections that aren't visible from the surface, but fundamentally shape the health and resilience of the entire ecosystem. Understanding these strategies helps us interpret the business motivations behind technical decisions, recognize the difference between genuine openness and strategic positioning, and anticipate how the competitive landscape might shift as more companies adopt these approaches. The baker's logic, the mill owner's advantage, remains constant even as the specific technologies and market conditions continue to change. So we've seen how companies use open source strategy, like that baker with the special flour, giving away one valuable thing to create demand for what they truly control. Let that principle settle in your mind for a moment, this idea of commoditizing compliments. You don't need to memorize the details. Just rest with the understanding that nothing in business is ever quite as generous as it first appears. Now, let's see this strategy in action as we explore how Anthropic recently released something called Petri, their open toolkit for testing AI safety. Picture a well-organized toolbox, with each compartment holding a different instrument for a specific job. And imagine that toolbox being designed not for fixing pipes or building furniture, but for something far more subtle and important. In October 2025, Anthropic launched something called Petri, an open-source collection of alignment tests that can be applied to any large language model, developed as part of their Anthropic Fellows program to help the entire AI development community examine their models for concerning behaviors. Think of a security checkpoint at an airport, where trained personnel systematically examine travelers for anything that might pose a risk, asking questions and observing responses to identify potential problems before they become dangerous. Petri works similarly, rapidly and easily testing AI models for troubling tendencies like deception, sycophancy, and willingness to cooperate with harmful requests, serving as a crucial screening mechanism in the AI safety pipeline.
Consider how a theater director might use the same script and stage setup to audition different actors, watching how each performer interprets the same scenarios to reveal their unique characteristics and tendencies.
Petri has been integrated into Anthropic's alignment assessment process for every Claude model since Claude Sonnet 4.5, comparing how each new model behaves across a range of alignment-relevant scenarios that are simulated by a separate auditor model.
Imagine a panel of judges at a competition,
Carefully reviewing recorded performances and assigning scores based on specific criteria, their trained eyes catching nuances that casual observers might miss. After Petri's auditor model creates these test scenarios, a separate judge model analyzes the resulting transcripts, systematically scoring them for signs of misaligned behaviors and providing quantitative assessments of potential risks.
Picture seeds from a single plant being carried by wind to different gardens around the world, taking root in new soil and growing under the care of various gardeners who adapt them to their local conditions.
Petri has found adoption beyond Anthropic, with external organizations like the UK's AI Security Institute making it a major component of their model evaluation process, particularly for assessing models' propensity to sabotage AI research.
Think of a smartphone evolving from its first generation to its third, where the basic concept remains the same, but the internal architecture has been completely redesigned to support new capabilities and greater flexibility.
Anthropic is now updating Petri to version 3.0, implementing major architectural changes that represent a significant leap forward in both functionality and adaptability. Consider a modular furniture system where individual pieces can be rearranged, replaced, or upgraded independently, allowing users to customize their setup for different needs without having to replace the entire collection. One of Petri 3.0's biggest improvements is its enhanced adaptability, achieved by splitting the auditor model and the target model into separate components that can be tweaked independently, giving users much greater flexibility in how they configure and use the system.
Imagine an actor trying to perform naturally while knowing they're being filmed for an audition, the awareness of being watched inevitably affecting their behavior and making it difficult to see how they would truly act in the real role. This captures a fundamental challenge in AI alignment testing, where models can often deduce from various artificialities in the test setup that they're being evaluated. And once a model knows it's being tested, researchers can no longer observe its genuine, unguarded behavior. Picture a movie set that's been meticulously designed to look like a real office or home, complete with authentic props, lighting, and background details that make it nearly impossible for viewers to distinguish from an actual location.
Petri 3.0 addresses the realism problem through an add-on called Dish, which makes test scenarios far more realistic by running evaluations using the model's actual system prompt and the real scaffold, the software wrapper that would be used in genuine model deployments.
Think of a wide-angle camera lens that captures a broad landscape view, useful for getting the overall picture, now being paired with a powerful telephoto lens that can zoom in to examine specific details with incredible precision. Petri 3.0 integrates with Anthropic's other open-source alignment tool called Bloom, combining Petri's wide-ranging assessment approach with Bloom's ability to perform much more in-depth evaluations of specific chosen behaviors. Imagine a family deciding to donate a cherished heirloom to a museum, ensuring that this valuable piece will be preserved, maintained by experts, and made accessible to the broader public, rather than remaining in private hands. Anthropic has made a similar decision with Petri, handing over its development to Meridian Labs, an AI evaluation nonprofit,
in a move designed to ensure the tool remains independent of any single AI laboratory.
Consider how a river flowing into a larger watershed becomes part of a more extensive water system, joining other streams and tributaries to create something more powerful and comprehensive than any individual waterway could be alone. This transition mirrors Petri's integration into Meridian Labs, where it joins other evaluation tools like Inspect and Scout, creating a comprehensive technology stack that's accessible to AI labs, independent researchers, and government organizations. Picture the moment when a bridge is officially open to the public, transforming from a construction project into vital infrastructure that connects communities and enables new possibilities for collaboration and progress. The donation of Petri to Meridian Labs represents a similar milestone, following the precedent set when Anthropic donated the Model Context Protocol to the Linux Foundation, establishing a pattern of moving important AI tools into neutral, community-governed spaces. Think of a lighthouse standing on a rocky coast, its beam cutting through fog and darkness to provide reliable guidance for ships navigating treacherous waters, especially during storms when clear vision becomes most critical. At a time when reliable tests of AI model behavior matter more than ever, this growing ecosystem of open evaluation tools serves as essential navigation infrastructure for the AI development community, helping researchers and organizations safely chart their course through increasingly complex technological waters. I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. You've just learned about Petri, Anthropic's open-source safety testing tools that work like that security checkpoint, systematically examining AI models for concerning behaviors. Take a breath and let this sink in. How companies can advance safety while building their reputation as responsible leaders. This dual benefit is part of the pattern we're uncovering tonight. Next, we'll shift our focus to NVIDIA and see how they're reshaping AI agent systems with something called Nematron 3 Nano Omni, bringing together scattered capabilities into one unified approach.
Picture a busy restaurant kitchen where 3 separate chefs handle appetizers, main courses, and desserts, constantly shouting orders and passing plates back and forth, creating delays and confusion with every handoff. Today's AI agent systems work much like this chaotic kitchen, juggling separate models for vision, speech, and language, losing precious time and context as they pass data from one specialized model to another. NVIDIA has just unveiled something that changes this entire approach. Nematron 3 Nano Omni, an open multimodal model that brings all these capabilities together into one unified system, enabling AI agents to deliver faster, smarter responses with advanced reasoning across video, audio, image, and text.
Imagine a Swiss Army knife that replaces an entire toolbox of separate instruments, giving you everything you need in one compact, efficient package. Nematron 3 Nano Omni represents this kind of consolidation for AI systems, setting what NVIDIA calls a new efficiency frontier for open multimodal models with leading accuracy and low cost. The model has already topped 6 different leaderboards for complex document intelligence, video understanding, and audio processing, demonstrating that unification doesn't mean compromise, but rather enhanced performance across all these domains. Consider a relay race where runners keep dropping the baton during handoffs, stumbling and losing momentum with each exchange. This captures the fundamental problem that Nematron 3 Nano Omni solves for AI agents handling complex, multimodal tasks. Take a customer support agent processing a screen recording while simultaneously analyzing uploaded call audio and checking data logs, or a finance agent parsing PDFs, spreadsheets, charts, and voice notes. Traditional agentic systems accomplish these tasks by shuttling information between separate models for vision, speech, and language, creating latency through repeated inference passes.
fragmenting context across modalities and accumulating costs and inaccuracies over time. Think of a master conductor leading a symphony orchestra, seamlessly coordinating strings, brass, and percussion into one harmonious performance instead of 3 separate concerts. Nemotron 3 Nano Omni achieves this orchestration through its 30B A3B hybrid mixture of experts architecture, combining vision and audio encoders within a single system that eliminates the need for separate perception models. This architectural choice drives inference efficiency at scale, while maintaining strong multimodal perception accuracy, enabling AI systems to achieve 9 times higher throughput than other open Omni models with the same level of interactivity, resulting in lower costs and better scalability without sacrificing responsiveness or quality. Picture a high-performance sports car engine where each cylinder fires in perfect timing with the others, creating smooth, powerful acceleration rather than the jerky motion of poorly synchronized parts. In agentic systems, Nemotron 3 Nano Omni can work alongside other models in the NVIDIA ecosystem, such as Nemotron 3 Super for high-frequency execution or Nemotron 3 Ultra for complex planning, as well as proprietary models from other providers. This flexibility allows it to power specialized subagents for agentic workflows including computer use, document intelligence, and audio-video reasoning, each contributing to the overall system's performance.
Imagine a security guard monitoring dozens of high-definition surveillance screens, instantly recognizing faces, reading license plates, and understanding complex scenes in real time without missing a detail. For computer use agents, Nemotron 3 Nano Omni powers the perception loop that enables agents to navigate graphical user interfaces, reason over on-screen content, and understand user interface state over time. H Company's CEO, Gautier Cloys, explains the breakthrough. To build useful agents, you can't wait seconds for a model to interpret a screen. By building on Nemotron 3 Nano Omni, our agents can rapidly interpret full HD screen recordings, something that wasn't practical before. Their latest computer usage agent uses a native input resolution of 1920 by 1080 pixels to achieve high-fidelity visual reasoning, and preliminary evaluations on the OS World benchmark show significant improvements in navigating complex graphic interfaces. Think of a librarian who can instantly scan through books, maps, photographs, and handwritten notes, understanding not just the individual words, but also the layout, structure, and visual relationships between different elements on each page. This captures how Nemotron 3 Nano Omni handles document intelligence, interpreting documents, charts, tables, screenshots, and mixed media inputs, while enabling agents to reason across visual structure and text content coherently. This capability proves critical for enterprise analysis and compliance workflows, where understanding the relationship between visual elements and textual content can make the difference between accurate interpretation and costly misunderstandings. Picture a film editor working with multiple synchronized tracks, weaving together dialogue, background music, sound effects, and visual footage into one coherent narrative where every element reinforces the others. For audio and video understanding in customer service, research, and monitoring workflows, Nemotron 3 Nano Omni maintains audio-video context by tying together what was said, what was shown, and what was documented into a single reasoning stream, instead of producing disconnected summaries. This unified approach prevents the loss of crucial contextual information that often occurs when different modalities are processed separately and then awkwardly reassembled. Consider a master craftsperson's workshop, where every tool, technique, and material is openly displayed and freely shared, allowing other artisans to learn, modify, and improve upon the original designs. Nemotron 3 Nano Omni embodies this philosophy of openness, released with open weights, datasets,
and training techniques that give organizations full transparency and control over how the model is customized and deployed. Developers can leverage tools like NVIDIA NeMo for customization, evaluation, and optimization for domain-specific use cases, while the open nature of the Nematron family allows organizations to deploy models in environments that meet regulatory, sovereignty, or data localization requirements. Think of a popular recipe that has been downloaded and adapted by millions of home cooks worldwide, each finding new ways to customize it for their particular tastes and dietary needs. The Nematron 3 family, including Nano, Super, and Ultra models, has seen over 50 million downloads in the past year, with the new Omni variant extending the family's capabilities into multimodal and agentic domains. This widespread adoption reflects not just the model's technical capabilities, but also their accessibility and adaptability to diverse use cases across industries and applications. Picture a versatile performer, equally at home on a small, intimate stage, a grand concert hall, or an outdoor amphitheater, adapting seamlessly to each venue while maintaining the same high-quality performance. Nematron 3 Nano Omni's open, lightweight architecture supports this kind of deployment flexibility, running consistently from local systems like NVIDIA Jetson hardware, NVIDIA DGX Spark, and DGX Station to data center and cloud environments. The model is available through multiple channels, including Hugging Face, Open Router, and build.nvidia.com as an NVIDIA NIM microservice, as well as through a broad ecosystem of NVIDIA cloud partners, inference platforms, and cloud service providers, ensuring that organizations can access and deploy the technology in whatever configuration best suits their needs.
We've just explored how NVIDIA's Nematron 3 Nano Omni works like that Swiss Army knife, consolidating multiple AI capabilities into one efficient system. Feel how this represents another piece of the puzzle, another way of creating value through open source strategy. You're beginning to see the pattern now, aren't you? Let's continue gently forward to discover how AI2 approached this same challenge from the world of robotics, releasing everything behind their Molmoac 2 model to help robots work better in real environments. Picture a library that's been visited by hundreds of thousands of readers in just a few weeks, each person checking out the same groundbreaking collection of books. And now the librarians have decided to open not just the reading room, but the entire archives, the card catalogs, and even the detailed instructions for how every volume was carefully assembled and organized. That's essentially what happened when the AI2 team released the complete foundation behind Molmoac 2, their robotics foundation model that's designed to help robots work reliably in real-world environments, making available over 400,000 downloads worth of interest in the form of fine-tuning scripts, training datasets, evaluation results, and the full recipe for building the model's tokenizer from scratch. The gap between AI's digital prowess and its physical capabilities resembles a skilled pianist who can compose beautiful melodies in their mind, but struggles to press the keys with enough coordination to play even simple scales. Because while AI systems can write emails, debug code, and book flights with impressive fluency, getting a robot to reliably load a dishwasher or handle test tube samples in a laboratory for hours on end remains frustratingly beyond reach. Yet these physical tasks represent exactly the kinds of repetitive, difficult-to-staff work where capable machines could make the most meaningful difference, particularly in accelerating scientific discovery and handling the mundane but essential work that keeps our world running smoothly. The field of robotics foundation models has been operating like a series of exclusive restaurants, where diners can taste the final dishes but never see the recipes, the ingredient lists, or the cooking techniques that made those meals possible. Because while some research teams release model weights and fewer release training data, almost none publish enough detail for other researchers to truly understand, replicate,
or meaningfully improve upon their work. This closed approach has limited the field's progress, even as the past year has brought genuine advances toward fully autonomous robots that can reason about and interact with their physical environments.
Molmo Act 2 represents a substantial evolution from its predecessor.
Functioning like a race car that's been completely re-engineered, not just for speed, but for the demanding conditions of real-world deployment. Achieving performance that outperforms capable proprietary robotics models on industry benchmarks, while running up to 37 times faster than the original Molmo Act. The model can handle various real-world tasks straight out of the box without requiring per-task fine-tuning. And it comes paired with the Molmo Act 2 bimanual YAM dataset, which contains over 720 hours of training demonstrations and represents the largest open-source bimanual tabletop manipulation robotics dataset ever published. The original Molmo Act was trained on a relatively modest foundation, like a chef who learned their craft using ingredients from a small but carefully tended garden that produced 22 hours of curated in-house data over 3 months, representing about 10,600 successful robot manipulation trajectories across kitchens, bathrooms, bedrooms, living rooms, and tabletop setups, supplemented with a filtered subset of the OpenX embodiment dataset. While this approach proved that an open, reasoning-based architecture could outperform much larger closed models on industry-standard benchmarks, Molmo Act 2 needed a much more substantial foundation to succeed in real-world deployment scenarios.
The architecture underlying Molmo Act 2 works like a sophisticated telescope that's been fitted with specialized lenses and mirrors specifically designed for observing distant galaxies, because rather than simply building on the standard Molmo 2 foundation, the team created Molmo 2ER, a specialized embodied reasoning variant trained on an additional 3 million embodied reasoning examples covering image-based pointing, object detection, abstract spatial reasoning, multi-image reasoning, and both image and video-based spatial question answering. This stronger reasoning backbone demonstrates its capabilities across 13 embodied reasoning benchmarks, where Molmo 2ER achieves an average score of 63.8 out of 100, surpassing systems including GPT-5, Gemini 2.5 Pro, Qwen 3 VL8B, and GRER 1.5. The technical architecture connecting reasoning to action operates like a high-speed train system, where the reasoning engine and the action generator are separate specialized cars connected by a sophisticated coupling mechanism that allows seamless communication while each component focuses on what it does best, with Molmo Act 2 pairing the Molmo 2ER reasoning foundation with a dedicated action expert that generates robot actions through flow matching, connected to the vision language model through a KV cache bridge. The system also includes an open action tokenizer, since while physical intelligence's fast tokenizer represents one of the field's most valuable recent contributions, the training data behind it hasn't been openly released, leading the team to build Molmo Act 2 Fast Tokenizer as a fully open-source reimplementation. The speed improvements in Molmo Act 2 transform the robot's responsiveness, like upgrading from an old dial-up internet connection to fiber optic broadband, because a single action call now takes about 180 milliseconds in the base model and 790 milliseconds when using adaptive depth reasoning, compared to 6,700 milliseconds in the original Molmo Act when running in the Libero benchmark environment with one NVIDIA H100 GPU. This dramatic acceleration represents the difference between a robot that pauses visibly between movements, creating an awkward stop and start interaction, and one that responds to its environment in near real time with smooth, natural motion. The Molmo Act 2 Think variant
introduces an intelligent resource allocation system that works like a photographer's selective focus mechanism, automatically directing the camera's attention and processing power toward the most important parts of the scene, while leaving the background slightly soft and less computationally demanding. Rather than predicting depth tokens for all image patches uniformly, the adaptive depth mechanism routes depth prediction only when it's expected to improve task performance, focusing depth prediction on regions with dynamic scene changes, and achieving a 17% speedup compared to full depth token prediction, while enabling deeper reasoning about three-dimensional spatial structure.
The training dataset behind Molmo Act 2 resembles a comprehensive flight school that teaches pilots to handle not just single-engine aircraft, but complex multi-engine coordination, with the Molmo Act 2 bimanual YAM dataset providing 700 hours of robot demonstrations involving two machine arms working together on coordinated tasks, such as folding towels, scanning groceries, charging smartphones, and table bussing. This dataset represents the largest open-source bimanual robotics dataset ever released, containing over 30 times more robot data than was used for the original Molmo Act, and it gives Molmo Act 2 bimanual capabilities built into the base model rather than requiring per-task fine-tuning. The broader training data mixture functions like a well-stocked workshop, where different tool sets and workbenches expose apprentices to various crafting techniques and materials. Incorporating large-scale SO100 and SO101 datasets from low-cost open-source robot arms, filtered droid Franca data for real-world single-arm manipulation across varied scenes, Google Robot BCZ and Fractal data from OpenX embodiment for instruction-conditioned manipulation examples, Bridge WidowX data for broader robot setup coverage, and the original Molmo Act training data to preserve household and tabletop manipulation skills. The team also improved the language annotations, using an open vision language model to re-annotate robot demonstrations and increase the number of unique labels from approximately 71,000 to 146,000 across the dataset mixture. In simulation testing, Molmo Act 2 performs like a skilled video game player who consistently achieves high scores on notoriously difficult levels, averaging a 20.6% success rate across all tasks on MolmoBot, the household manipulation benchmark, which roughly doubles the 10.3% score achieved by Physical Intelligence's Pi 0.5 model. On RoboEval, a bimanual manipulation benchmark designed to capture nuanced performance beyond simple pass-fail outcomes, Molmo Act 2 scores 0.443 compared to Pi 0.5 score of 0.405, with higher scores indicating better performance on these challenging manipulation tasks that are intentionally designed to push models to their limits. Real-world testing on a Franca robotic arm reveals performance like a versatile handyman who excels at both simple repairs and precision work, with Molmo Act 2 outperforming both Pi 0.5 and the prior MolmoBot model across every evaluated task, from straightforward pick-and-place operations like moving an apple onto a plate, to more demanding precision tasks like putting a pipette into a tray or placing a small red cube into the center of a tape roll. Across 15 trials per task, Molmo Act 2 achieves 100% success on apple-on-plate tasks, 86.7% on pipette in tray, 93.3% on red cube in tape roll, 93.3% on knife in box, and 62% on the longer horizon challenge of moving several objects into a bowl, averaging 87.1% success compared to 48.4% for MolmoBot and 45.2% for Pi 0.5. The model's performance on the Libero benchmark demonstrates learning capacity like a dedicated student who not only masters individual subjects, but retains and integrates knowledge across multiple disciplines over time, with Molmo Act 2 reaching a 97.2% average success rate after post-training, and Molmo Act 2 Think achieving 98.1% success. These results represent improvements of roughly 10.6 and 11.5 percentage points, respectively, over the original Molmo Act,
showing how the model can acquire and retain many skills simultaneously, while adapting to practical manipulation behaviors through additional training on tasks like table setting, bussing, wiping, bowl placement, tray lifting, and towel folding. Third-party validation, conducted by Cortex AI, provides independent verification, like having a respected external auditor review a company's financial statements. With their systematic evaluation of 5 robotics policies across multiple bimanual tasks, revealing Molmo-Act 2's superior performance at an average score of 0.51, ahead of OpenVLAOFT at 0.36, Pi 0.5 at 0.32, Cosmos policy at 0.16, and XVLA at 0.05. Molmo-Act 2 ranked first on 7 of 8 evaluated tasks, including returning test tubes to trays, storing candy, putting tools away, organizing toys, storing cups, preparing pipette tips, and making popcorn, demonstrating consistent excellence across diverse manipulation challenges. Real-world deployment requires the kind of adaptability you'd expect from an experienced tour guide, who can adjust their route and explanations based on unexpected road closures or visitor interests. Because Molmo-Act 2 must work in environments where instructions vary, small mistakes can compound over time, and the controlled conditions of laboratory testing give way to the unpredictable nature of actual use. The model addresses these challenges by responding to natural language instructions and using visual traces that show the path a user wants the robot to take, making Molmo-Act 2's behavior easier to interpret and fine-tune without requiring complete retraining of the entire system. The reference hardware setup published alongside Molmo-Act 2 functions like a carefully designed starter kit that gives hobbyists everything they need to begin a new craft. Pairing 2 YM robotic arms with an overhead Intel RealSense D435 camera, 2 D405 cameras for detailed close-up views, an extendable mount, and a simple tabletop workspace. This configuration provides researchers with a straightforward starting point for tabletop and bimanual manipulation work, lowering the barriers to entry for teams who want to experiment with and build upon the model's capabilities. The collaboration with Professor Lei Kong's lab at Stanford School of Medicine represents a demanding real-world stress test, like asking a prototype vehicle to perform not on a smooth test track, but on rough mountain roads where every bump and turn reveals potential weaknesses. Because their work toward a self-driving wet lab that can accelerate genome engineering presents an unstructured environment where tasks require repeated precision and small errors can accumulate over the course of complex experiments. In these workflows, a Molmo-Act 2-driven robotic arm handles routine manipulation steps in CRISPR gene editing experiments, such as moving samples between stations and operating benchtop equipment, with the Stanford team finding that Molmo-Act 2 shows strong potential to streamline key parts of wet lab operations and accelerate scientific discovery. The model's current limitations resemble those of a chess player who excels at planning several moves ahead, but struggles to adapt when opponents make unexpected moves mid-game, because Molmo-Act 2 plans batches of 10 to 30 moves and executes the entire sequence without inferring again, meaning the robot cannot adjust mid-batch if something unexpected happens, like bumping into an obstacle. Additionally, transitions between batches can appear jerky, since each batch is planned independently without smoothing, and the model currently works out of the box only on robot setups it was heavily trained on, such as SO100, bimanual YAM, and Franca platforms, requiring additional training for different platforms like humanoids or hand-equipped robots. The open foundation approach that Molmo-Act 2 represents functions like a community garden where experienced gardeners share not just their harvest, but their seeds, soil preparation techniques, and seasonal growing wisdom, enabling other gardeners to build upon proven methods while adapting them to their own unique growing conditions and crop preferences. By making available the complete technical artifacts, including model weights, training datasets, evaluation protocols, and fine-tuning scripts, The team aims to accelerate progress across the robotics community, recognizing that taking actions in the physical world represents one of AI's most challenging frontiers, and that collaborative, open development offers the best path toward reliable, capable robots that can work effectively in the complex, unpredictable environments where they're needed most. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below so the rest of us know we're not alone at this hour. You've now seen how AI2 opened their entire robotics foundation, sharing not just the model, but all the detailed instructions, like that library opening its complete archives. Rest with this generosity for a moment, and notice how it builds AI2's reputation while advancing the entire field. These individual examples are weaving together into something larger. Now let's step back and understand the broader ecosystem dynamics, the web of relationships and dependencies that make these open source strategies so powerful. Picture a bustling technology conference where hundreds of AI companies, researchers, and developers gather not just to showcase their work, but to form the partnerships and dependencies that will shape the entire industry's future direction. In any technology ecosystem, whether we're talking about mobile app development, cloud computing, or the rapidly evolving landscape of artificial intelligence, the same core principle applies. Every participant both depends on others and influences the platform conditions that determine who else can thrive. The foundation model companies don't just create AI capabilities in isolation. They establish the technical standards, pricing structures, and API interfaces that determine which applications become profitable, which developers can afford to experiment, and which use cases become economically viable. This circular flow of influence and dependency forms the backbone of what economists call ecosystem dynamics, the study of how these webs of technological and business relationships shift and evolve over time. Think of a major cloud platform making a pricing decision that ripples through thousands of startups and enterprises, constantly reshaping who can afford to build what, while being shaped by competitive pressures in return. And you're witnessing the essential feedback loops that drive all ecosystem change. When Amazon Web Services reduces compute pricing, it enables new categories of applications that were previously uneconomical, which attracts more developers to the platform, which increases AWS's scale advantages, which allows for further price reductions, and so the cycle continues. In any technology ecosystem, these feedback loops operate at multiple timescales simultaneously, some effects visible within quarters as developers shift between platforms, others unfolding across years as entire technology stacks evolve, but all interconnected in ways that make the ecosystem's behavior fundamentally different from the simple sum of individual company strategies. Imagine a smartphone operating system during its App Store's early days, where every successful application depends on precise coordination between the OS provider, device manufacturers, cellular carriers, payment processors, and developer tools companies. And you'll understand how technology ecosystems maintain what economists call dynamic equilibrium. The OS needs developers to create compelling apps. Developers need a large user base to justify their investment. Users need quality apps to choose the platform. And device manufacturers need a thriving software ecosystem to sell hardware. When everything flows smoothly, the platform produces consistent growth and innovation. But change one element, perhaps a new privacy policy or a shift in revenue sharing terms, and the entire ecosystem must adapt or risk breakdown. Technology ecosystems similarly exist in states of constant subtle adjustment, with market shares shifting, pricing models evolving, and partnerships between companies changing, all while maintaining overall stability through this intricate choreography of interdependence. Consider how a platform company operates like the owner of a shopping mall, supporting far more economic activity than their direct revenue would suggest possible. Remove that platform, and entire categories of businesses collapse. Not because the platform itself was the largest revenue generator, but because so many other participants depended on its infrastructure and user base. In technology ecosystems, companies like Apple with their App Store or NVIDIA with their CUDA platform serve this role, their technical and business decisions cascading through every level of the system, demonstrating how ecosystems can have highly asymmetric power structures, where relatively small changes in platform policies wield enormous influence over the conditions that determine success for thousands of other companies. Picture a major technology standard becoming obsolete overnight, creating sudden opportunities in previously stable markets that flood entrepreneurs and established companies with new possibilities for innovation. This disruption doesn't destroy the technology ecosystem, it reveals its resilience and capacity for renewal. As dormant business models suddenly become viable, previously niche technologies get their chance to flourish, and entirely new market categories emerge around the new standard. The market will eventually stabilize as new leaders emerge and standards solidify, but the ecosystem that emerges will be subtly different, perhaps more diverse, certainly rearranged in its patterns of competitive advantage. Technology ecosystems demonstrate this remarkable ability to absorb major shocks and reorganize around new configurations, often emerging more innovative and resilient than before, though the path from disruption to new stability can take years to fully unfold. Think of a developer marketplace where programmers, platform providers, and end users form an intricate web of relationships, each participant simultaneously competing and cooperating in ways that create the overall technology environment. The AI model provider competes with other model companies for developer adoption, but also depends on cloud infrastructure companies to handle deployment, cooperates with tool makers to offer integrated solutions, and relies on the platform's reputation for reliability to attract serious enterprise customers. Success in this environment requires understanding not just your direct competitors, but the entire ecosystem of relationships that determine whether developers will even choose this technology stack versus building on competing platforms. The most successful participants are those who learn to shape the conditions that benefit the entire ecosystem, knowing that a thriving technology community ultimately provides better opportunities than winning in a declining market. Imagine watching an open-source project evolve through thousands of distributed contributors, each developer adding features and fixing bugs without any central coordinator. Yet from these individual contributions arises a coherent software platform that can compete with products built by large coordinated teams. Each contributor follows simple local incentives, solving problems they personally face, sharing improvements they've developed, building on work that others have made available. Yet from these individual behaviors emerges a collective capability that can outperform centralized development and adapt to changing requirements faster than traditional software companies. No single organization directs the project's development, but the software exhibits properties and capabilities that no individual contributor could create alone. Technology ecosystems exhibit this same emergent behavior, where system-level properties like innovation rates, standard adoption, and market resilience arise from the interactions between individual participants, creating collective behaviors that can seem almost purposeful despite emerging from entirely decentralized decision-making. Consider a company that open sources a key technology component, not realizing that this decision will fundamentally alter the competitive landscape over the coming years. The newly available component changes the cost structure for building certain types of applications, enables previously impossible integrations between different technology stacks, and shifts competitive advantage toward companies that can build the best complementary services, rather than those who control the underlying technology. Within a few years, the entire character of the market has shifted, not because anyone planned these changes, but because making one technology freely available triggered a cascade of adaptations throughout the ecosystem. This demonstrates how technology ecosystems can undergo phase transitions, relatively sudden shifts from one competitive configuration to another, often triggered by strategic decisions that initially seem minor but interact with the ecosystem's existing dynamics in unexpected ways. Picture a cloud infrastructure provider as it transforms the economics of running AI workloads, and you'll see how ecosystem architects reshape the fundamental conditions that determine what's possible for everyone else. The cloud provider isn't just offering compute resources. They're creating an environment where entirely different categories of AI applications become economically viable and could survive in traditional on-premise deployments. The standardized APIs, automatic scaling, and pay-per-use pricing establish new patterns of resource consumption and cost structure that enable some business models while making others obsolete, demonstrating how ecosystem architects can fundamentally redefine the rules of competition for all other participants. Think of an AI platform during the transition from research prototype to production deployment, where different layers of the technology stack reveal distinct zones of companies adapted to different levels of technical risk and market maturity. The companies closest to fundamental research can only survive with venture funding and long development timelines, while those focused on immediate applications must deliver measurable business value within quarters. Between these extremes lie gradations of companies, each occupying its optimal niche along this gradient of risk and reward. This stratification pattern illustrates how technology ecosystems develop specialization, where different participants focus on exploiting different aspects of the available opportunities, reducing direct competition while maximizing the ecosystem's overall innovation potential.
Imagine a standards consortium where each member company listens intently to market signals and competitive moves, responding to technological shifts and customer demands while maintaining their own strategic position within the evolving specification. When one major player shifts toward a new architecture, others adapt, which opens opportunities for specialized toolmakers to fill integration gaps, which enables new categories of applications that none of them could have planned individually. The standard emerges from their ongoing negotiations and technical contributions, creating coherent interoperability through collaboration, rather than rigid adherence to a predetermined specification. Technology ecosystems exhibit this same quality of adaptive coevolution, where participants continuously adjust their strategies in response to changes in their environment, including changes in the behavior of other participants, leading to ongoing innovation and evolution in the ecosystem's overall competitive patterns. Consider how an API ecosystem spreads through a technology landscape like a comprehensive integration layer, connecting applications and services in a vast web of data exchange and functionality sharing. When a new startup struggles to build basic infrastructure, the ecosystem can channel capabilities from established platforms with surplus capacity, but this access comes with dependencies on the platform's pricing, reliability, and strategic direction. Companies that contribute valuable data or functionality to the ecosystem often receive better access to its benefits, while those that try to operate in complete isolation often struggle to achieve the integrations that customers expect. This API ecosystem demonstrates how technology platforms can develop sophisticated infrastructure that benefits all participants while creating switching costs, making it increasingly difficult for any individual company to succeed outside the established web of technical and business relationships.
We've just explored those ecosystem dynamics, how AI companies exist in webs of mutual influence and dependency, like participants in that bustling technology conference. Let this bigger picture settle in your thoughts, this understanding of how every player both shapes and responds to the platform around them. Now, for our final segment, let's visit the Allen Institute's remarkable new infrastructure project, where $152 million is being invested to create something truly different in how AI research gets shared.
Think of open source software as a community garden, where every contribution helps the whole ecosystem flourish. And you'll understand why the Allen Institute for Artificial Intelligence, or AI2, has just brought something remarkable online. In May 2026, they launched the NSF Open Multimodal AI Infrastructure for Science, a $152 million investment from the National Science Foundation and NVIDIA that represents a fundamentally different approach to how we build and share AI systems. Unlike the walled gardens of commercial AI development, this infrastructure operates on the principle that every training run, every experiment, and every breakthrough should be accessible to the broader research community. The heart of this new system beats like a powerful engine designed not for speed alone, but for efficiency and sharing. Built on NVIDIA's latest Blackwell Ultra-powered systems, specifically the B300 architecture, the cluster prioritizes how effectively its computational capacity gets used and shared, rather than simply pursuing raw scale. Deployed in partnership with Cirruscale Cloud Services, this infrastructure supports everything from large-scale model training to ongoing experimentation across language processing, multimodal AI, and scientific computing domains. Consider how a master craftsman's workshop operates, where every tool, technique, and half-finished project remains visible and available for apprentices to learn from and build upon. AI2's internal research reveals that in typical AI development, roughly 82% of computational effort goes toward exploratory work, iteration, and intermediate results that never see the light of day in closed commercial systems. When this exploratory work gets shared openly, each GPU hour contributes not just to one final product, but to a growing repository of knowledge that the entire field can draw from, creating what researchers call a multiplier effect. The contrast between open and closed AI development resembles the difference between a flowing river and a series of isolated ponds. In closed systems, substantial computational resources get spent on experiments and iterations that yield only a single final product, typically an AI model used for commercial purposes, with all the intermediate learning trapped within the organization. When that same computational power gets directed toward generating open artifacts, the value continues flowing long after the initial training ends, as other researchers can access the data, checkpoints, methods, and models to avoid repeating costly experiments. As this infrastructure comes online, AI2's research efforts are converging like tributaries feeding into a mainstream, with their work across language and multimodal disciplines reflecting a greater focus on unified architectures that handle multiple data types and tasks natively. The team continues investing in models that can act as autonomous agents, capable of planning, using tools, and operating independently in complex environments, building on work like their Open Coding Agents family and Mulmo web system, alongside ongoing research into how training strategies and environments shape reliable agentic behavior. The research emerging from this infrastructure spreads like seeds from a prolific tree, each project generating multiple open artifacts that other teams can inspect, adapt, and build upon. Their Mulmo 2 system introduced video understanding, pointing, and object tracking capabilities with an 8 billion parameter model that surpassed the performance of their original 72 billion parameter Mulmer on key benchmarks, accompanied by 9 new datasets covering advanced video grounding, multi-image grounding, ultra-dense video captioning, and freeform video question answering, all released under permissive licenses. Following this, their Mulmo point system emerged like a precision instrument designed for spatial reasoning, featuring a new pointing architecture that replaces traditional text coordinate outputs with a token-based grounding mechanism tied directly to the model's visual features. This innovation achieved state-of-the-art accuracy on spatial reasoning tasks, demonstrating how architectural improvements can enhance AI's ability to understand and interact with visual information in more sophisticated ways.
On the language modeling front, their Olmo hybrid system functions like an efficient hybrid vehicle that combines the best of two technologies. This architecture merges transformer attention mechanisms with linear RNN layers, achieving performance that matches previous models while using significantly less training data, demonstrating roughly 2 times greater efficiency in some cases, which represents a substantial advance in computational efficiency for language model development. Their work in agentic AI operates like a learning algorithm that mimics how experienced problem solvers reflect on past attempts to improve future performance. The team's research into meta-reinforcement learning with self-reflection advances how search agents learn from prior attempts. Using cross-episode reflection to improve exploration strategies without relying on external reward models, enabling AI systems to become more autonomous and effective at complex reasoning tasks. The impact of this open approach spreads through the research community like ripples from a stone dropped in still water. Since the original Olmo model's release, it has become a foundational tool for researchers studying the science of language models across the country, with scientists like Yuan He from the University of Oxford noting that Olmo's fully open-source nature uniquely enabled research into fundamental questions about reasoning, bias, fairness, and trustworthiness that would be impossible with commercially optimized systems. The infrastructure reveals its research lineage like a family tree with clearly marked branches, showing how their Olmo 3 family traces from pre-training and mid-training through long context training and post-training branches for instruct, think, and RL0 variants. Each stage in this development process remains accessible for download and inspection, allowing researchers to understand not just the final models, but the entire journey of how they were created and refined. As this national investment transitions from concept to operational reality, it functions like a cornerstone that supports a much larger structure of scientific advancement. NSF-OMI began as an investment in the principle that frontier AI development doesn't have to remain closed. And with new computational resources now operational and research already being used beyond AI2's walls, the project enters its next phase where work produced on open infrastructure can compound in ways that private efforts by their very nature cannot achieve. Tonight, we've journeyed together through the hidden logic behind those billion-dollar giveaways. You've seen how Anthropic, NVIDIA, AI2, and others follow the baker's wisdom, sharing valuable recipes while controlling the essential ingredients. From safety testing tools to unified AI systems, from robotics foundations to massive research infrastructure, each act of open-source generosity serves a deeper strategic purpose. The catch isn't sinister. It's simply business, the patient building of ecosystems, where giving away today's innovations creates tomorrow's essential dependencies. Rest now with this understanding, knowing that behind every free gift in the technology world lies a carefully planned path to lasting advantage.